Now, what we have on this slide here is a series of metal carbonyl compounds. And really the first question is, what is the question? Any ideas? These are on this slide. What question am I going to ask you? Okay, that's a good question. Any more good questions like that one? What else could I ask you? I could ask you oxidation states, but I won't, because oxidation states are going to wait until the very end of this course so as not to confuse them with electron counting. What else could I ask you about these molecules? Yeah, well, most stable, possibly. What were we talking about at the end of the last lecture? Yes. The other question I could ask you is, which of these will have the highest CO stretching frequency, and which of these will exhibit the lowest CO stretching frequency? So let's do an electron count on these. Are any of these compounds here not 18? Okay, well, I don't see any hands, so I'm taking that to mean that everybody believes they are 18 electron compounds. These two we've encountered already. They are homoleptic metal carbonyl compounds, and as we stressed at the beginning of the last lecture, the homoleptic metal transition metal carbonyl compounds obey the 18 electron rule. This one, I don't know, can't remember whether we encountered or not. This is a metal carbonyl cation species, but manganese is in group 7. 7 plus 6 times 2 is 19, minus 1 because it has a positive charge. This 2 is an 18 electron compound. But I'm more interested in us reinforcing what we were doing in the previous lecture and asking the question, which of these compounds here is going to have, first of all, the highest value of carbon-oxygen stretching frequency in the infrared spectrum, and why? So 1 out of 3 chance of getting it right, but I'd like an explanation. The first one, which I take to be this one here, why? Well, and there's one other point that you've missed out, and it's positively charged. So those are all the explanations that we need. Bridging carbonyls, and there's a hint there for the next question, bridging carbonyls are found at lower frequency for a reason we'll come on to in a moment. But if we look at this manganese compound, the manganese compound, first of all, is not got any bridging carbonyl ligands. It's got 6 carbonyl ligands for the electron density that is present to be distributed across. So the amount of back bonding that you get is the amount of electron density on the metal divided by 6 carbonyl ligands. And how much electron density would that be, considering that the species is actually formally positively charged? So this would definitely have the highest carbon-oxygen stretching frequency. So I think we know what the answer to the next question, of which would have the lowest carbon-oxygen. The second one. And why? Because in the second one we have bridging carbonyl ligands. Bridging carbonyl ligands are experiencing back bonding from 2 different metal centres. So there's more back bonding. More back bonding means more occupancy of the pi star orbital. More occupancy of the pi star orbital means a lower carbon-oxygen bond order. And since we know that the frequency is proportional to the square root of the force constant or the strength of the bond, that will mean that they stretch at lower frequency. Let's see, what can we do with carbonyls apart from count their electrons and predict their IR spectrum? Well, we can use them as starting materials in more transition metal organometallic chemistry. And you can substitute carbon monoxide ligands for other ligands. And you can do that one of 2 ways. You can promote the process either thermally, which clearly means heating the solutions up, or photochemically, which means irradiating these samples with light. And someone asked me a little bit, why isn't there more mechanistic discussion in 2C32? Well, because it's quite difficult sometimes to get at the mechanisms of these reactions. But one point that should be fairly obvious to you in terms of how these substitution reactions are going to proceed. If you start off with a compound that is an 18 electron species, you're not just going to add a new ligand to it, because if you did, then you would become a 20 electron species or more, depending on what your ligand actually was. So that means that the mechanism of substituting a carbon monoxide ligand must be what we would call a dissociative mechanism. It must go through an intermediate which has lost a carbon monoxide ligand. So if we have an 18 electron species and we lose 1 carbon monoxide ligand, how many electron species is our intermediate? We should have our bits of paper handy if everyone wants to participate in a shy fashion. Get those out, but you know, someone, I think I heard someone say 16. Obviously, 18 minus 2 is a 16 electron species. This 16 electron species is clearly not going to be electronically satisfied as a 16 electron species and can gain another 2 electrons by interacting with a different ligand to carbon monoxide to make a new 18 electron complex. And that's going to be the mechanism of these sort of reactions. As a general rule of thumb, it is second row transition metals that react faster than first row or third row transition metals. So those of you who've done topic 1, can I have a show of hands? Who's done topic 1? Yep, a large number of you have done topic 1. Some of you, I guess, are halfway through topic 1, and so you will not have done the reaction whereby you actually do chemistry like this. In topic 1, you are substituting carbon monoxide ligands for tris-parazolyl borate ligand. Now, which metal do you use in topic 1? Molybdenum. Molybdenum is a second row metal, and it's not a coincidence that we're using molybdenum. We use molybdenum because if we were to use chromium, or we would use, what's the third row transition metal under molybdenum? Does anyone know? Tungsten, yes. If we were to use chromium or tungsten, then the reaction would be much slower. You would be looking at a 12-hour reflux instead of an hour reflux. And, you know, I don't think anybody would be happy with that. Certainly not the demonstrators, and very unlikely to be the students. Now, one of the questions that is asked in topic 1 that people discuss on these occasions is, what might be the intermediate? Well, generally, in these kind of reactions, you do these reactions in the presence of a solvent. And that solvent, to some extent, is going to be a base. It is not going to be as good a ligand as a carbon monoxide ligand. But if you kick out these carbon monoxide ligands, you know that carbon monoxide is a gas. It's not going to hang around. So the process doesn't tend to be reversible. Once you've removed carbon monoxide, it's not going to go back on again because it's lost from the solution as a gas. So we have these electron deficient species that have less than 18 electrons. They will bind the solvent molecule as a ligand, as a donor. And so if you do these reactions in acetonitrile, what you tend to find is that you do get an intermediate species, which would be a mono or bis or tricarbonyl compound with 3 acetonitrile ligands on it. So if it's 3 carbonyls left, you'll have 3 acetonitriles replacing it. These ligands are much less strongly bound than carbon monoxide. They're much less strongly bound than carbon monoxide, and therefore they're replaced really quite easily. So you can replace these ligands with a final substitution product very easily. And so one example of that is this molecule here. What's that molecule called? Well, it's cyclic, so it's cyclo. I think we can count, so it's got 7 members in it. It's cycloheptatriene. So this is cycloheptatriene. And cycloheptatriene will bind to a transition metal as a eta-6 ligand. Each one of these diene functions will donate 2 electrons to a transition metal center, and so we can produce a species like this 18 electron compound here. Now, this 18 electron compound here has 3 dienes coordinated to it, and then you're going to have a CH2 group, or methylene group, as perhaps these some things are sometimes called, out of this plane here. Now, these CH2 group can be treated with a reagent that will remove hydride ligands. So we're not deprotonating this, we are removing a hydride ligand from it. And a good reagent for removing hydride ligands is this one. This is the trityl cation, triphenyl carbenium tetrafluoroborate. This will remove H- from the species. And if you remove H- from cycloheptatriene, then you make a cycloheptatrienyl cation. A cycloheptatrienyl cation. Now, in terms of our electron counting and our organometallic chemistry, this is going to be an eta-7 bonded aromatic species here. So this is an eta-7 ligand bound to the chromium center. So if I was to ask you, what is the electron count? We've already established this is an 18 electron species. How many electron species is this one? Okay, this one seems to be producing considerable food for thought, and although the correct answers are in the majority, there are a lot of answers that are not quite right. So let's take ourselves through an analysis of this. Chromium is in group 6. So chromium is bringing 6 electrons to our count. We have 3 CO ligands. So I expect everybody is happy with that. So what we have is 6 plus 6 is 12 for this fragment here. Now, what I said when I presented the ligands table to you is when you're doing covalent electron counting, when you have these carbon-based ligands, all you need to do is count the number of carbon atoms that is interacting with the metal center, and that will tell you how many electron donor it is. So I made a point here saying that this was an eta7 cycloheptatrienyl cation. So that's it, 7. This is a 7 electron donor. 12 plus 7 is 19, but it's positively charged. The species is positively charged, so we remove an electron. And this is an 18 electron complex. The answer's not always 18, but you know, think very carefully before you commit yourselves to an answer that isn't 18. There will be questions where the answer is genuinely not 18. In fact, on this lecture, there will be questions where the answer is genuinely not 18. So that was thermal substitution, and typically these thermal substitution reactions are quite harsh conditions. We're refluxing these species in relatively high boiling solvents. So acetonitrile boils at about 100 degrees centigrade, I believe. I'm not exactly sure. These reactions are often done in solvents like N-octane. The boiling point of N-octane is 160 degrees. So you need quite harsh conditions if you are going to thermally substitute carbon monoxide ligands. If you want to do it under somewhat milder conditions, you need a more precise way of putting the energy into the system. And the way that you can achieve that is photochemically. So if you irradiate these species with light of sufficient energy to displace your carbon monoxide ligand, then you can do this under what otherwise are much milder conditions. And these reactions are frequently done in solvents, perhaps like acetonitrile, but an even weaker base than acetonitrile is THF. Now, I've asked you before, I think, what THF is. We all remember what THF is. Tetrahydrofuran is a cyclic ether, and the important bit for an inorganic chemist is that it is going to be a Lewis base through lone pairs of electrons on the oxygen atom. So what happens is we irradiate something like tungsten hexacarbonyl in the presence of THF, and we produce an intermediate. This intermediate has a very weakly bound THF ligand. It's bound to be formed first because you're doing this in bulk THF, where the concentration of THF is very high. But if you then introduce another ligand, that ligand will bind more strongly to a very labile. Labile means it comes off and goes on very easily THF ligand, and you will produce a new complex of these. So an example, a good example of this kind of chemistry comes in iron pentacarbonyl. Iron pentacarbonyl will react in the presence or under irradiation conditions with cis cyclooctene. So this is just a cyclic alkene ligand. So this cyclic alkene will displace one CO if you irradiate it with light. You can do that reaction again. You can add more cyclooctene and irradiate some more, and you can replace 2 of the carbon monoxide ligands with cyclooctene. But there's a very important point in this kind of chemistry, and that is, it's a general point in carbonyl substitution chemistry. It gets progressively more difficult to substitute carbonyl ligands. The first substitution may go fairly easily. The second substitution may go slightly more difficult. The third substitution will be more difficult still. Substituting beyond that point can become next to impossible. Why? Why do you think it is that substituting carbon monoxide ligands for other ligands becomes progressively more difficult the more times that you do it? Strength of the bonding of the carbon monoxide to your metal will depend on the donor interaction and the pi acceptor interaction. And of course the pi acceptor interaction, the strength of that interaction is a consequence of how much electron density is on the metal. So when you have 6 carbonyl ligands, what's happening is the electron density has been divided amongst 6 carbonyl ligands. And so the strength of the bonding is limited by the fact that it has to share the back bonding with 5 other carbonyl ligands. Now, as you substitute carbonyl ligands, most ligands are not as good pi acceptors as carbon monoxide. Carbon monoxide is a very good pi acceptor ligand. It accepts electron density from the metal very effectively, and it also doesn't donate electron density to the metal very effectively at all. If you substitute for a ligand like an alkene ligand is better at donating electron density to the metal and worse at accepting electron density from the metal. That has the effect of increasing significantly the electron density on the metal, which can then only be divided amongst the number of carbonyl ligands that are actually left. So it gets much harder to substitute carbonyl ligands because back bonding to the remaining carbonyl ligands gets much stronger. That's substitution of carbonyl ligands. What other kinds of chemistry are we interested in when we talk about metal carbonyl species? Well, there is a class of compounds called metal carbonyl anions, or sometimes called carbonyl metallates. I'm calling them metal carbonyl anions in this lecture course, but you might encounter the expression carbonyl metallate species. Now, how do we make these species? Well, obviously, I guess, reduction. We understand reduction as the addition of electrons. Occasionally, it's the addition of hydrogen to these species as well, but we understand reduction as the addition of electrons. So formally, of course, we are reducing the species if we're going from a neutral species to an anionic species, normally in these cases. Now, I really like this reaction here. This is a synthetic method for making a metal carbonyl anion, and it involves a disproportionation of this species we've encountered already, dimanganese decacarbonyl, in the presence of pyridine at 120 degrees centigrade. And it makes this species here the manganese pentacarbonyl anion. 2 equivalents of the manganese pentacarbonyl anion and 1 equivalent of this species here, manganese hexapyridine dication. Why does Dr. Lancaster like this reaction so much? Anybody prepared to speculate? This reaction encapsulates, this single reaction encapsulates the difference between Dr. Claydon's lectures and my lectures. This compound here is representative of the kind of compounds that you worked with Dr. Claydon. This compound here is representative of organometallic compounds. So what do I mean by that? Well, first of all, let's try the acid test. Remember I said to you when we were talking about the 18 electron rule, 18 electron rule is only useful, only going to work for organometallic compounds. It has no useful predictive value whatsoever in classical coordination chemistry, and Dr. Claydon gets quite annoyed when you try and apply the 18 electron rule to classical coordination chemistry. So what is the electron count? You can do the maths, but what is the electron count for the manganese hexapyridine dication? You've got your pieces of paper. What is the number? So pyridine, do we all know what pyridine is? Okay, let's remind ourselves of what pyridine is. So is that the piece of information that we need? Pyridine is a pretty typical dative donor ligand. It's a 2-electron donor. Okay, I see an answer. I see several answers now. And all the answers that I see are correct. So well done. What we have here is manganese. Manganese is in group 7. We have 7 plus 6 times 2 is 19. But of course, this is a dication, so we remove 2 electrons from this species. We'd have a 17-electron species. You can do the counting, but it has no significance because we wouldn't expect this species to fulfill the 18-electron rule. It is an example of a classical coordination compound. It's a 2+ cation, and in order to stabilize a 2+ cation, what you need is a good dative donor. And you've got a good dative donor here in the form of the pyridine ligand. The other species containing manganese here is quite different. The other species here is an 18 electron species, and it's actually got a formal oxidation state not of 2+, but of 1-. So it is the sort of species that can only exist stabilised not by a good donor ligand, but stabilised by a good acceptor ligand in the form of carbon monoxide. So that's why I regard this reaction as encapsulating the difference between Dr. Claydon's lectures and my lectures. How else can we make metal carbonyl anions? Well, we can do something that might be familiar to the organic chemist. We can do a nucleophilic attack on a coordinated carbonyl compound. And if you do that, what you produce is an intermediate that looks like this. So this species here is itself not at all stable, and it will decompose, losing carbon dioxide here, losing carbon dioxide to make this one, which I hope you can see on your slides, even if you can't see on the screen at the back of the lecture theatre. This is the sodium salt of the iron tetracarbonyl hydride anion. Now, note the name. This is a hydride anion. Remember in our formalism, a hydride ligand has an oxidation number of -1. Has an oxidation number of -1. So you might expect it to behave as an H- donor, or an H- type species. But if we take this species and react it with sodium hydride reacts as a base towards this compound, and what you see is elimination or removal of hydrogen and generation of a dianion. So although this is a hydride compound, it has reacted as though it's a source of protons. And that's one of the interesting features of these metal hydrides that we'll look at in a little bit in a moment. They are formally H- ligand complexes, but they often behave as acids, and that is slightly contradictory. How else can we make metal carbonyl anions? Well, you've seen these reactions already, essentially. If you do these kind of reactions like this one, if you take zirconium tetrachloride, we looked at titanium, I think. So if you take zirconium tetrachloride and use a reducing agent like potassium naphthalide in the presence of a crown ether to wrap around your potassium cation, then you can produce species like this one. So this is zirconium hexacarbonyl dianion. And remember, in the case of zirconium, because we're only starting with 4 electrons to begin with, then we have to go to a dianionic species in order to satisfy our 18 electron rule. We can't get more than 6 carbonyl ligands, so we can't keep pumping carbonyl ligands into the system. We can stop at 6, and then we need to accumulate negative charge in order to get to an 18 electron species. So that will be a zirconium hexacarbonyl dianion species. If you take this one, which is familiar to us all, this is the species that can exist as a couple of isomers, so dicobalt octocarbonyl, you can use sodium metal as a reducing agent in THF, and then what you produce is the sodium salt of the cobalt tetracarbonyl anion. Now, there is a general rule here that wherever you have species which have metal-metal bonds, so remember we had dimanganese decacarbonyl, we had cobalt octocarbonyl, wherever you have species that have metal-metal bonds, they are very easily reduced. So you can reduce those with alkali metals to produce the carbonyl anions. So wherever there is a metal-metal bond, those species react really very easily with things like sodium to produce carbonyl anion compounds. Now, these carbonyl anions are thermally stable, so you can get the right cation associated with these and you can put them in a bottle, you can keep them for long periods of time. But what you do have are relatively high-laying reactive pairs of electrons on the transition metal species, and so they do tend to be sensitive towards oxidation. So if you put something into your system that is a strong oxidizing agent, then it will frequently react with metal carbonyl anions. So we have to look out for that. So they're fairly thermally stable in the sense you can keep them, but if you put an oxidizing agent present, then they will react with it. Now, metal carbonyl metallates, or metal carbonyl anions, or here we are, the ever expression carbonyl metallates, are strong bases / nucleophiles. What we are looking at is essentially a transition metal with a pair of electrons on it. This transition metal with a pair of electrons on it will behave just like any other atom with a pair of electrons on it. It can function as a Lewis base, potentially. It can function as a Bronsted base. It can function as a nucleophilic reagent. So these transition metals can actually behave like nucleophiles and react with electrophilic reagents. What I want you to be able to do is to predict how basic or how nucleophilic your transition metal carbonyl anion is. So if you had to predict how nucleophilic a reagent would be, how would you do it? What would govern how strong a nucleophile something... Yeah, if you wanted to measure it, then you would say, does it react with a very weak electrophile? I take your point. If you're looking at a compound and you want to determine, if you want to see how strong a nucleophile is, essentially what you're asking yourself is, how high is the electron density on that atom? How nucleophilic, how basic is it? And so what we ought to be able to do is to look at the ligands on our transition metal anion and say, are those ligands electron donating ligands, in which case they're going to make the species more nucleophilic, or are they electron withdrawing ligands, in which case they're going to make the species less nucleophilic? And a carbon monoxide ligand is a very good electron withdrawing ligand because it's a pi acceptor ligand. A carbon monoxide ligand has the effect of essentially removing electron density from the metal because it's accepting it into its pi star orbital. The weakest bases are those that have the greatest number of carbonyl carbon monoxide ligands on them. So if we look at a scale of basicity, the cobalt tetracarbonyl anion, and this is a sort of archetypical metal carbonyl anion, this species has a relative basicity of 1 on our scale. So obviously we've defined it as such. If you take a compound like cyclopentadienyl iron dicarbonyl, cyclopentadienyl iron dicarbonyl anion, that has a relative basicity of 7 times 10 to the 7 times as basic as your cobalt tetracarbonyl anion. So why on earth is it so much more basic? Well, it's so much more basic for 2 reasons. Firstly, a cyclopentadienyl ligand, which we will come on to, is a much better donor and a much worse acceptor. So a cyclopentadienyl ligand is putting a lot more electron density onto that metal center. And secondly, we've only got 2 carbonyl ligands left on this iron complex, only 2 carbonyl ligands to remove electron density from the center, whereas in the cobalt compound you've got 4 carbonyl ligands removing electron density. So you can see massive differences in the basicity of these species depending on what the ligand set is. And when we're looking at more and more ligands in this course, we will look at them in terms of whether they're good donors, in which case they're going to make electron density on the metal higher, or good acceptors, in which case they're going to drop electron density on the metal. Now, there is a fundamental principle of chemistry that goes way, way, way beyond organometallic transition metal compounds, and in fact you wouldn't first have thought of it in those terms at all. And that is, if something is a very strong base, what can you tell me about its conjugate acid? So if something is a very, very strong base, its conjugate acid is going to be very weak. And of course, if something is a very, very strong acid, what does that tell you about its conjugate base? It's very, very weak. And so a couple of examples that you will all be happy with illustrate this point, and that's what I've put up on the whiteboard over here. Let's take the example of the acid-base equilibrium for methane. Not something you probably spend all that long thinking about. Methane is in theory in equilibrium with a proton and a methyl anion. Now, of course, we wouldn't have encountered methyl anions at all until we started talking about organometallic chemistry, in the case of species like methyl lithium. And we can recognize that methyl lithium is a very, very strong base because we know that its conjugate acid is a very weak acid. You don't normally regard methane as being an acidic species. But it is theoretically impossible to deprotonate methane and its conjugate base would be the methyl anion species. So this is a combination of a very weak acid and a very strong base. Another one that you're very, very familiar with here is sulfuric acid. Now, everybody here regards sulfuric acid, I suspect, as a very strong acid. And of course, this equilibrium here, certainly in aqueous solution, lies very firmly on the right-hand side of this species. Why is it that it lies so very firmly on the right-hand side? It's because the conjugate base is a very weak conjugate base. And the reason that the conjugate base is a very weak conjugate base is because, well, you tell me, why is this such a weak conjugate base? It's not a long time ago since you covered this. Yes, because the negative charge can be delocalized onto the available oxygen atoms. So this is a very weak base, meaning this is a very strong acid. So the two things go hand in hand on opposite parts of the exchange. So if you can regard a carbonyl ligand as being a little bit like the sulfur-oxygen functionality here. A carbonyl ligand is doing the same thing. You can't necessarily draw a resonance form, although some people would draw a resonance form delocalizing the negative charge onto the carbonyl ligand, but it is having exactly the same effect. The carbonyl ligand is withdrawing electron density from the metal center and therefore rendering the metal center as a weaker base. Right, I've said briefly on this lecture course that, of course, an inorganic chemist is only as good as what he can do for his organic chemistry friends. And so these metal carbonyl anions are useful in organic synthesis. And I suspect that Dr. Stevenson, if he hasn't already done so, will probably touch upon a little bit of ion chemistry at some point during your chemistry degrees, because that's one of his specialities. These species here are very good nucleophiles. And as very good nucleophiles, they will react with all sorts of electrophilic species. So electrophiles that will be very familiar to you, like alkyl halides they will react with. They will react with acid chlorides, as obviously examples of very reactive electrophilic species. They will also react, perhaps not quite as obviously, with additional carbon monoxide. So what happens is if you pressurize one of these species with carbon monoxide, you get migration. So what happens if you pressurize alkyl carbonyl anion with carbon monoxide is you will get migration of the alkyl group to an equivalent of coordinated carbon monoxide. And if you do that, then you are making the equivalent of an acyl group here. So you've formed a carbon-carbon bond in this system, and not only a carbon-carbon bond, but a terminally functionalized carbon-carbon bond. And if you want to liberate this species, you can do it relatively easily. So there's a lot of functionality. This is a sort of illustration of the versatility and the usefulness of these reagents, rather than a core part of 2C32 that I would examine you on. I've already hinted at the existence of conjugate acids for these metal carbonyl anion species. How do you make these species? Well, obviously you can protonate your metal carbonyl anion. So if you protonate your metal carbonyl anion, then you can produce a species that gets called a metal carbonyl hydride. So we are adding a proton and making something that is formally a metal carbonyl hydride. So this is just a name, remember? When you're assigning oxidation states, you regard that bond as being broken heterolytically to give you H- and metal plus. That's the formalism that we use. It does not necessarily mean that the compounds behave as sources of H-. Here's the one that's hopefully becoming familiar with this. Cobalt tetracarbonyl anion will react with sulfuric acid to give us the cobalt carbonyl hydride species, and of course the sodium salt of hydrogen sulfate in these systems. Now, when you do this, you obviously need to recognize that you need a source of an acid. And my advice to you is to use a strong acid. My advice to you when you're looking at reactions like this is to use a strong acid. Of course, how strong an acid you actually need to get these reactions to proceed would depend on how basic your carbonyl anion is. The more basic your carbonyl anion, the weaker acid you require. But if you want to be sure that your acid is strong enough to protonate just about any metal carbonyl anion, then use a strong acid like sulfuric acid in these systems. What you then end up with here is a volatile liquid. So this compound is a volatile liquid. H2 ion CO4 is a volatile liquid. The problem with these volatile liquids is they're not particularly stable. They tend to decompose very easily, losing carbon monoxide. And once they start to lose carbon monoxide, this process can become almost autocatalytic, and you get runaway decomposition to the metals. The way to stabilize these compounds is to keep them under an atmosphere of carbon monoxide. So there it becomes unfavorable for them to lose carbon monoxide, and if they do, they can pick another one up very quickly and stay as stable 18 electron species. So these are fairly sensitive, need to be kept under carbon monoxide and atmosphere. And what you find is that the stability of these compounds increases from the first row to the third row. So the most stable examples of metal carbonyl hydrides are third row element complexes. If you look at compounds of the first row transition metals, they tend to be really poorly stable and definitely require these protective atmospheres. Now, I find this quite an intriguing reaction here. If we start off with iron tricarbonyl bis triphenyl phosphine compound, that's an 18 electron compound. If you react it with sulfuric acid, you protonate it, and you go from a 5-coordinate iron compound to a 6-coordinate iron compound. But what's the electron count of this iron compound here, this cationic species? What is its electron count? How many d electrons has iron got? 8. Okay, so iron has got 8. A CO ligand is a how many electron donor? 2. So we've got 3 times 2. And a phosphine ligand, let's see how we're working. How many electron donor is a phosphine ligand? Good, very good. Okay, so 2 times 2. I say very good, not because I'm trying to patronise, but because many times students do get confused until they got a little bit of practice. It's one of those things that I find in examinations, phosphine ligands tripping people up, but clearly not you lot. So we've got here 4 from this species. Right, how many electron donor is a hydride ligand? 1. Very good. And what have we missed out so far? Positive charge. So we have a positive charge in this species, so that's obviously going to be -1 in this system, giving us a grand total of 18. So well done to everybody who predicted this as an 18 electron species. I just find this slightly interesting, the idea that you're actually adding a ligand and you keep your electron count exactly the same in this system. But if you think about it, it makes perfect sense, because how many electrons does a proton have? It has no electrons at all. It has 0 electrons. So if you add a proton to a compound, then you shouldn't expect its electron count to increase in these systems. What other mechanisms do we have for making these things? Well, metal carbonyl hydrides, again, these reduction type reactions. Here, by reduction, what we mean is we're actually introducing hydrogen in these, because we're not actually changing electron counts in these species very much. So if you start off with the iron tetracarbonyl diiodide compound here, then what you do is you react that with, so sodium borohydride is something you've encountered before. Here it is effectively acting as a source of H-, and we are doing a metathesis reaction. We are exchanging I- for H- in this reaction, and in so doing we produce same compound we've already encountered here. We produce our iron tetracarbonyl dihydride species. This is a slightly more interesting reaction here. If you start off with chromium hexacarbonyl, 18 electron chromium hexacarbonyl, and you react that with another source of H-. These reagents have an interesting name. What you tend to have is 3 ethyl groups on the boron and 1 hydride. And these are very good reagents for donating H- species. So good, they are called superhydrides. That's the commercial name. It's not my expression. The commercially, these things are called superhydride. So this is a source of H- just like BH4 was a source of H- for us. And what happens initially is the H- nucleophilically attacks a coordinated carbonyl ligand to give us a very unstable intermediate like this one. Then you get rearrangement and you get elimination of CO in these species and a new compound which has a bridging hydride ligand. This bridging hydride ligand, how many electron donor is it? It's a 1 electron donor. Don't be tempted to draw a dative bond here. There's no lone pair of electrons on the hydrogen to donate. So this is a 1 electron donor. And so this is a good one. What is the electron count for this species here? So we need to do an electron count with respect to 1 chromium complex. What is the electron count? I don't want the electron count for both ends. I want the electron count with respect to 1 of these chromium species. Okay, we'll have a few answers. Some people seem to be hedging. That's no good. We can't have that. Get off the fence. Right, so let's have a look at this, shall we? Because I think it is a nice one. Chromium is in group 6, okay? I'm going to take that one as red, and I'm also going to take it as red that our CO ligand is a 2 electron donor, so we've got 5 times 2 here. So let's say this is D6. I normally like to draw these things. So this is 6, this is going to be 10, so that's a 16 electron compound up to that point. Now what we have here is a bridging hydride ligand, but this bridging hydride ligand is shared between 2 chromium centres, isn't it? So what we've got here is half of a hydride ligand. So that's going to be half an electron. This is only a formalism at this point. There is no such thing as half an electron, but we'll see if we end up with a total that is half an electron, then we are definitely got a problem. So there's a half here. Is there a charge on this species? There is. So the charge is -1, but of course half of it belongs on 1 chromium and half of it belongs on the other chromium. So we've got negative charge here, so half of this negative charge is half an electron, half here. If we top this lot up, we get to 17. So this is a real compound, and it is a 17 electron compound. So this is very unusual. This species here is very, very, very odd. And nevertheless, it is real, it exists, and you would arrive at an electron count of 17. Right, finally, I think for making these things, there is a very important reaction that we will come back to right at the end of this course, and that is the reaction that makes transition, or one of the reactions that makes transition metals very special. And that is the ability of transition metal organometallic compounds to react with hydrogen. And we've had these kind of discussions many times. Is hydrogen a reactive molecule? Well, of course, hydrogen will explode if you ignite it in the presence of oxygen. But in many ways, dihydrogen is not a reactive molecule. You can't just take hydrogen and an alkene together and expect to form an alkane. It does not happen in the absence of a catalyst. So hydrogen is not really a particularly reactive molecule. And yet transition metal species can take hydrogen at room temperature or even below room temperature, and they can activate it. They can do chemistry with it. And that's really very, very important, because there are so many industrial processes that have at the heart of them the catalytic activation by transition metals of dihydrogen. And so this key step in these processes is often something like this. So what we've got here is dimanganese decacarbonyl. Dimanganese decacarbonyl is another one of these, well, we've mentioned it several times. It is a metal-metal bonded species. And so far in this lecture, I've said that these metal-metal bonded species are very easy to reduce with alkali metals. They also have another important property. They react with hydrogen gas. So where you have a metal-metal bonded species, they tend to be particularly reactive, and they react with hydrogen. And when they react with hydrogen, they form metal carbonyl hydride species. So what you get are two equivalents of a metal carbonyl hydride species from these metal-metal bonded compounds. And that is special. You know, main group elements won't, as a rule, do this. Only transition metals will react under such mild conditions with hydrogen, and that is the basis of many catalytic processes. So what you find in these species is, if you look at the oxidation state of the manganese here, the manganese in dimanganese decacarbonyl, the oxidation state is 0 in this species. The oxidation state in the product is +1. So this is why this is an example of oxidative addition. So what it's essentially doing is taking the pair of electrons that's making the manganese-manganese bond and the pair of electrons that's making the hydrogen-hydrogen bond, and it's taking one electron from the hydrogen-hydrogen bond, one from the manganese-hydrogen bond, and forming a manganese hydride bond, and doing exactly the same on the other side. So it is not a heterolytic bond cleavage process, it's a homolytic bond cleavage process. The reactivity slide is just an illustration of what you can do with these. It's not something that I expect everybody to memorize. I hope you're interested, but I don't expect you to memorize this. This is just a summary. We've already talked about this. If you have a species which has lots of carbonyl ligands on the metal carbonyl hydride, those are electron withdrawing. They will have the effect of stabilizing the conjugate base. If you stabilize your conjugate base, you are going to make your carbonyl hydride a better acid. So the more carbonyl ligands you have on your carbonyl hydride, the fewer electron-donating ligands like cyclopentadienyl ligands or electron-rich phosphine ligands, the stronger your acid will be. And the easiest way to consider why it's going to be a stronger acid is because it will have a weaker conjugate base. That's how I tend to think about these things. Look at the equilibrium. If you can stabilize the base, then you make the acid stronger. And that's essentially what we're illustrating on these species. So although we call them metal carbonyl hydrides, when you dissolve them in solution, they dissociate to give a carbonyl anion and a proton. They do not dissociate to give a metal cation